let's begin. Dhruv, can you hear me okay? All right, I think this most of you have done, but there are probably still 20 odd of you who have still not enrolled on Piazza. So if you have not, please do that as soon as you can. And again, you need to upload a scan of the signed syllabus form. And again, there was some confusion that that's not automatically graded. I actually have to manually go and grade it. So if you submit and don't see a score, that's because I've not gotten around to it. The Autolab FAQ page is already up. It might not be complete, so if there's a particular question that you think should obviously be in there but is not in there, there's a post on Piazza, so just put in a comment and we'll try to include it. The TA office hours will be finalized by Monday. And the first TA office hours will start from Tuesday, which is fine because Monday is off anyhow. I wanted to comment on two things regarding the programming aspects of this course. The first thing you have to realize is that programming is only worth 12% of your entire grade. Okay? And designing algorithms on paper or kind of the pseudocode or doing proofs is worth 82% of your grade. So that should give you an idea of how much time you should be spending on programming questions versus non-programming questions. The reason why I mention it is because it's very easy to get sucked into programming questions. You say, oh, I'll only do 2 hours, and then this happens and that happens, and you're down that rabbit hole and you're spending like 5-6 hours on question 1. And that is not a good use of your time. Right? You should be spending more time on question 2s and 3s on the homework, not only because they're worth 60% of your homework points, but because all of the exams, there will be no programming questions on the exams. It will be all algorithm design and proof based. Okay? So invest your time wisely, and don't take this the wrong way in the next statement, but 331 is not the place to learn a new language. Okay? There was some confusion. Starting with homework 1, you will also have the choice of C++, right? So pick one of C++, Java, or Python. Pick the one that you're most comfortable with and stick with it throughout the semester. That's not to say you cannot learn a new language. If you want to, that's fine, but it's not advised because you're going to put in a lot of time trying to learn it. Not only that, there are strict rules about what sources you can use and cannot use, and I think learning a new language with those source restrictions placed is not the best way to learn a new language. Okay? Any questions on this? All right, so last time we kind of looked at this problem of increasing broadband access. We kind of narrowed problems to smaller sub-problems, and then we came up with this flow chart of various steps in algorithm design, which we're going to go over and over again. You will be sick of this pretty soon, but I'll still keep on showing you the flow chart. Okay, so we always start off with a problem statement. Typically, it's real world problem. What that means is typically it's stated in English. It's not that precise. So the next thing you have to do is come up with a precise mathematical definition, right? So that's the first step you'll do. Then from that, once you have precisely and mathematically defined the problem you want to solve, then we'll go into designing algorithms. Right? And for this course, an implementation of algorithms will be designing data structures. So there will be things like you'll say, do this operation when you're thinking about designing the algorithm, but maybe you'll not spend that much time thinking of what data structure to use. Okay? So we're going to do it in 2 steps. First, design the algorithms where the certain you might not make the final decision on data structures yet, and then do it. Okay? That's not to say that is the best way to do this. In real life, both should go hand in hand. Is that in this course, I want to focus more on the algorithmic concepts than the data structures, and that's why it's kind of separated that way. Not coincidentally, it also happens that the textbook does it the same way too. Okay? And then we're going to analyze this algorithm, and that's basically will mean two things. We'll analyze the correctness of the algorithm, which means we're going to argue that for all possible inputs, the algorithm behaves like it should. And then we're going to do runtime analysis. We're going to say on the worst case input, we're going to come up with an asymptotic bound on the runtime. Okay? Any questions on this flowchart? Yeah, Evan.
Oh, wow, that's super cool. What do you mean by precise mathematical definition?
Right, so Evan's question was, what do you mean by precise mathematical definition? Okay, I'll give you an example next, and then we'll see. So we're going to start off with a real-life application, and then we're going to spend pretty much all of today coming up with a precise mathematical definition. Okay. But in general, what it means is you have to formally define what your input is, formally define what your output is, and then what is, on this input you need to get this output, so that mapping. So these are the three components that we'll do. Any other questions? All right, so how many of you have heard of the National Resident Matching Program before this? Okay, so this is probably one of the earliest applications of algorithms that have been going on for a while. And this is the procedure by which doctors are assigned residencies once they finish their MD. Okay? So let's go through an example. So it's completely made up examples. In particular, all the doctors are fake, or not fake, screen doctors, right? So we'll just see a bit of pop culture, I guess. How many of you know who this character is? Any guess on which show, if not the character?
Grey's Anatomy.
Yeah, it's Grey's Anatomy. It's Melinda Bailey from Grey's Anatomy. House. Scrubs, JD. All right, so these are the three doctors who are interested to come to some hospital in Buffalo. How many of you know what these hospitals, hopefully not too many of you know hospitals that well, but so the first hospital actually doesn't stand anymore. I made the slides in 2007. I've just been too lazy to move it. But this is in Gate Circle near downtown Buffalo General, which is no longer standing. Oh no, sorry, the middle guy, Millard Fillmore, doesn't stand. So there are three doctors who want to come to Buffalo for their residency, and there are three hospitals that are interested in having residents. And so you somehow want to assign doctors to hospitals. So what can go wrong? So let's say, I forget the name. So Millard Fillmore Suburban makes an offer to House. House doesn't have any offer from Buffalo, but he really wants to come to Buffalo, says, okay, fine. And so they come up with an agreement, right? And then Buffalo General realizes House has come to Buffalo, and so they send him an offer saying, a better offer saying, why don't you come to us? And House is like, all right, fine, that works. So we'll get over there. Now, let's say Bailey gets hired by Gate Circle, but now Suburban doesn't have any doctors. And they're like, oh, Bailey's coming to Buffalo, let's make her an offer. Right? So they make her an offer. And as you can see, this can just keep on going forever and ever, right? So everyone's making offer and counter offer. Probably good for the doctors. Maybe they're getting paid, get higher and higher salaries, but definitely not a good situation to be in. Okay? And National Resident Matching Program doesn't happen with 3 doctors in Buffalo. It happened with basically every doctor that's graduating in a given year in the entire country. So you don't want kind of these kind of instabilities or assignments changing all the time. So what happens is all the doctors who are up for residency send in their preferences for what hospitals they want to go to this central entity called the National Resident Matching Program. The National Resident Matching Program then sends information about the doctors to the hospitals. And then the hospital sends back their preferences on the doctors. Okay? So at this stage, NRMP has the preferences from the doctors. It also has preferences from the hospitals for each of them. And so then what it does come up with a matching. Right? But I mean, the situation that I showed earlier could still hold if they don't do a good job, right? So this led to what's known as the stable matching problem by David Gale and Lloyd Shapley. I forget who, one of them won the economics Nobel Prize, partly for this work. Okay. So this is what I would say, Evan, is like a real life problem. I actually haven't even told you what is the quality that you need from matching the things. So it's pretty vague, right? So now we want to make this more precise. So that's kind of, and the way we're going to do it is in 2 steps. We're going to make it somewhat precise and then really, really formal. Okay. Any questions before we go on? Yeah.
What do you mean by preferences?
Right, so Evan's question is, what do you mean by preferences? We're going to define it formally, but essentially each doctor ranks the hospital, saying this is my most preferred to least preferred, and hospitals rank doctors from preferred, least preferred, sorry, most preferred to least preferred. All right, so let's try to make this problem slightly more precise. So what do we have? We have a set of employers, let that set be E, and we have a set of applicants, let's call that A, and each employee or potential employee, each employer has a preference list on all the other applicants, and each applicant has a preference list on all the employers. And you want an assignment of applicants to employers that is stable. In other words, you don't want this mad thing of offers and counter offers happening all the time. Ideally, and not ideally, this is what you want. An assignment is stable if no one has any incentive to break off from their current assignment. Again, this is vague. We're going to make it a bit more precise, but that's what we're going to do. So in other words, here's what I mean by it's stable. You look at each employer, each applicant X and each employer Y, such that they're not assigned to each other. Okay, so you're picking any applicant and an employer so that they're actually not assigned to each other. And this is considered stable if for each such pair at least one of 2 things hold. Either Y, which is the employer, prefers every candidate that it has accepted to X, right? So the way to think about this is X might want to go and say to Y, hey, why don't you give me an offer? But Y should say, well, you know what? All the employers, applicants that are assigned to me, I prefer them to you, so no. Or X would prefer her current employer to Y. So you could think of a reversing happening. Employer Y trying to poach away X, but X says, well, my current assigned employer, I'm much more happier with them than you, so I won't. Okay, so for any employer-applicant pair that is not matched, at least one of them has an incentive not to get assigned to the other one. Okay? All right. So I'll let you read this for a bit. So there are 2 things out of this. One is Python is great, but again, as I said, if you don't know Python, 331 is not the best place to learn Python, but you should learn Python at some point of time. The other is simplicity, right? You want things to be simple because it makes for life much easier. And especially when it comes to modeling real life problems mathematically, at least at the first step, it would make sense for you to simplify the problem a bit. Okay? And why is that? Well, because in real life problem, you might have like 20 requirements that you want to handle. Right? And if you start coming up with a mathematical problem that has 20 variables in it, your head will just start exploding. Right? So the idea always is to simplify things to begin with, try to see if you can solve it. If you can, then that's when you start expanding out. Okay? So what we're going to do is make some simplifying assumptions on the problem that we talked about. And so here are some questions that you might want to think about when you start to try to simplify it even more. So we talked about preferences, but how do we specify it, right? How many employers and applicants are in this problem? Right? Is it the case that there are way more employers than applicants, or way more applicants than employers? Because that could make a difference of how you're designing your algorithm. And I say you assign. What does an assign mean? Formally, what does it mean? Right? And depending on if there are more applicants versus employers or not, can an employer get assigned more than one applicant? And can an applicant have more than one job? So can they be assigned to more than one employer? And then we said every employer has a preference on the applicants, and every applicant has preference for the employers. Do they have to rank everyone? Or can they just say, I only care about these 5, the rest I really do not want? Right, so is your preferences, mathematically the first one is it a total order or is it a partial order? Can it be the case that it's kind of the dual of these two questions? An employer doesn't get assigned any applicant, or an applicant doesn't get any job. And as you can imagine, the answers could be different depending on the application that you're looking at, right? And I'm going to actually tell you how we decide on these questions, and you could ask why. And the answer is, well, the way we are doing it, it probably simplifies the problem to its core. So that's kind of the simplest version of the problem, where all the kind of interestingness of the problem still remains. Right? So we're going to design an algorithm that solves this very special case, but then we'll see you can kind of extend that algorithm to solve the more general cases too. Okay? So even though it is possible in real life for employers to have more than one employees or hire more than one applicant, or people to have more than one jobs, we're going to assume that that's not going to be the case. Okay, so everyone gets assigned as more. Every employer gets assigned at most one applicant, and every applicant gets assigned at most one job. And no one gets left out. So every employer gets at least one applicant, and every applicant gets at least one job. So what these 4 mean is every applicant will get assigned exactly one employer, and every employer will get assigned exactly one applicant. If that is the case, what do you think the ratio between the employers and applicants should be? I have to ask your name.
Matt.
Sorry?
Matt.
Matt. You're Matt too, or Mark? Sorry.
I'm Mark.
You're Mark, sorry. Okay, Matt.
I'm Matthew. It's
Matt.
1-on-1.
1-on-1, right? Because every employer has exactly one applicant, and every applicant has exactly one employer, so you can't have more applicants than employers, or vice versa. So we're going to assume that they are actually exactly equal, 1-on-1. Okay. So the other question is, how do you specify preferences? Is it fully specified, or can you partially specify it? We'll insist that the preferences are completely specified, right? So every applicant, and not only is it completely specified, there's no ambiguity. It has to be strictly ranked. You cannot say, an employer cannot say, well, applicant 1 or 2 are the same, I don't care. Well, you have to, right? So it has to be a complete ordering from most preferred to least preferred. Okay? And similarly for applicants. How we define preference lists, we're just going to come up with a list, and so we'll see soon how we do that. And formally, what's an assignment? This might be the most obvious of all of these questions. As I said, everyone gets assigned to employer exactly one employee, one employer exactly one applicant, and vice versa. But mathematically, this is what's known as a perfect matching. Okay, so we're going to define a perfect matching to deal with that. Okay. Are there any questions on the questions, or the answers that we came up with? I have to ask your name first.
Lloyd.
Sorry?
Lloyd.
Lloyd. Yeah.
So a perfect match is everyone has an assignment?
Perfect matching is everyone gets matched to exactly one other.
So no one's empty.
No one's empty and no one has more than one.
So how's it different from stable?
Well, I have not defined it yet. Right? So yeah, so I actually not even defined what a perfect matching is formally. So that's why I said I'm actually not done defining the problem. This was the first cut of simplifying things. Now I'm going to spend the rest of the time completely formalizing the problem for you. Okay. I have to ask your name first.
Alex,
Alex.
why is the ratio 1 to 1?
I asked the question, why is the ratio 1 to 1? I said just a simplifying assumption. It turns out that the algorithm that we are going to design works easily as well for any other ratio. So just a simplifying, it's just one variable, less variable to keep in mind. But that assumption is without loss of generality. It's fairly easy to generalize. Okay, where are we? Okay, so we talked about employers and applicants, and there is a traditional way to define this problem, which has its advantages and disadvantages. The main disadvantage is not really a feminist formulation, and for that I apologize. But here's how people have defined it historically. There are n men and n women, 1-to-1 ratio between employers and applicants, and they have preferences for each other. And each has a preference list. And so you want to match them, or if you were even older, marry them off in such a way that's stable. Right? So you want to match them in such a way that there's no unmatched pair that would prefer to be each other than their current assigned partners. And again, we're going to define this formally. So it will turn out that defining formally would just mean I'm going to list, I think, 6 or 7 definitions, right, one after the other, which can get a bit boring. So what I'm going to do is informally define all things first via examples, and then we're going to go on and formally define everything more. So we're going to look at examples when n equal to 3. How many of you know this show? Yeah, okay. How many of you know? Can I have a raise? Oh yeah, the rest of you should go and see this series. So it's Firefly, and the 3 men are Mal, Wash, and Simon, and the 3 women are Inara, Zoe, and Kaylee. A valid matching, which is different from a perfect matching, and this again is a mathematical definition. What this says is every man is assigned to at most 1 woman, and every woman is assigned to at most 1 man, right? So this is a valid matching, again, not a perfect matching, but a valid matching, because Simon and Zoe are not assigned to him. This is not a matching because Mal is matched to 2 women, and that's not allowed. Perfect matching, every man gets assigned exactly 1 woman, and every woman gets assigned exactly 1 man. Okay, so this is a valid perfect matching. And as part of your question 2 on the homework, if you attempted it, you had to argue that if you had n men and n women, then you had n factorial many possibilities. So in this case, it's 3 factorial, 3 times 2 times 1, 6. So there are 6 possible perfect matchings in this case. So we also, as I said, have preference lists, and what that means is, let's say Mal's preference list is Inara is most preferred, followed by Zoe, followed by Kaylee, and Kaylee's preference list, say, is Mal, followed by Wash, followed by Simon. And so what an instability would mean in this scenario is something like this. So let's say this is a perfect matching, and on your right-hand side are their preference lists. Then we say the pair Wash and Zoe forms an instability because they both are higher on the preference list than their current assigned partners. So Wash is currently assigned Kaylee, but if you go to Kaylee, Wash's preference list, Zoe comes before Kaylee. Right? Zoe is currently assigned Simon. If you go to Zoe, Wash comes before Simon. So this is not a stable match. Okay? And the way we are going to formally define stable matching is defining formally what a not stable matching is. So we're going to define the negation just because it makes the definition slightly easier. Okay. Questions, comments? I'll leave it over here. Let me know. I need to set up for a bit. But all right. So let's start with this. So as I said, the problem that we're going to look at is called the stable matching or marriage problem. Again, not an ideal setting, but that's what it is. So what do we have in this problem? We are going to have n women and n men. Okay. So we're going to have n women. We're going to denote this set of women by capital W. And that's the set, and we're going to number, we're going to label the women as W1 to Wn. By the way, if there's any notation that I'm using that you're not familiar with or have forgotten, please do ask. I'm happy to clarify. Similarly, you have n men. M1 to Mn. Okay. Thank you. This is capital M. Yeah, otherwise there are issues. All right, so we're going to have a running example of n equal to 2, where the set of men is Brad Pitt and Billy Bob Thornton, and the set of women is Jennifer Aniston and Angelina Jolie. How many of you know all the 4 names? Oh boy, I need to start updating my examples. Okay, how many of you know at least one of these 4 names? Okay. All right, so our first definition would be of a matching, and a matching is just a subset of pairs of men and women, right? So a subset as this notation saying this set is a subset of M cross W, if you remember, is a Cartesian product, right? So this is defined as, if you don't remember, is the pair of all M comma W's. Okay. So a matching A is a subset, so or a subset is a matching if every man is assigned or every woman is assigned at most one man. So for all women W, there exists at most one man M such that M comma W belongs in this set of pairs. And for all men, there exists at most one woman W such that M comma W is in S. Okay. So I've just written down formally what we've already said. Every man gets assigned at most one woman, and every woman gets assigned at most one man. Okay. And then what I said, a perfect matching. Which is the same as above, but the at most gets replaced by exactly. So every man is assigned exactly one woman, and every woman is assigned exactly one man. Okay. All right, so let's do some quick examples. So the way I'm going to define these pairs is for each man, I'm going to draw a circle with the name in it. So Brad Pitt and Billy Bob Thornton, and then Jennifer Aniston and Angelina Jolie. And if there is a pair M comma W, I'm just going to draw a line between them. So I'm just kind of drawing a graph for this. All right. So is this a matching? Yes, right? Everyone's assigned exactly one. Is this a perfect matching? Yes, everyone is assigned exactly one. All right, let's look at another example. Again, the same four people. Oh, by the way, I guess most of you don't know this. This used to be a valid matching in real life at a certain point of time. Okay. All right. Is this a matching? No, because Angelina Jolie is assigned to two men. Is this a perfect matching? No. So one thing to note is every perfect matching is also a matching, but not the other way around. Right? So if a given set of pairs is not a matching, it cannot be a perfect match. Okay. Another example. Is this a matching? Yes, right? So there are Billy Bob Thornton and Angelina Jolie are not assigned anyone, but that's okay because matching says at most one. Harshita. Ah, what's your name? Sorry? Kishan.
This example is for any man. Is it possible that the number of men and women are not the same and you still have a match?
So Kishan's question is, if the number of men and women are not the same, can you have a matching? Yes, but you cannot have a perfect matching. But for this problem, we are always assuming the men and women are the same. Okay. All right. So this is a matching. Is this a perfect matching? No. Right? Because there's Angelina Jolie and Billy Bob Thornton are not matched. All right. One final example. Is this a valid matching? How many say no? How many say yes? Majority is not always right, but in this case it is. So an empty set is a valid matching because everyone is assigned at most one man or woman, which in this case just happens to be 0. It's allowed. But this is not a perfect matching because everyone's assigned 0 men. So this is a valid matching, but not a perfect matching. And as I just said, on question 2 in homework 0, you argued there are n factorial perfect matchings on n men and n women. By the way, n factorial grows very, very quickly. If you have not done this, if you just try to compute n factorial in a computer, it will crash pretty soon. Okay. All right. Any questions so far? All right, so we are not quite there yet to define a stable matching because we have to talk about preferences first. So we're going to quickly define preferences and then finally define a stable matching. So we're going to look at a preference list. And what this is for every woman W, you'll have a preference list which we're going to denote by L of W, which is just a total ranking of every other man. So total ranking of all men. And when I say total ranking, I mean it's a strict ordering. Right? So 1 is better than 2, 2 is strictly better than 3, and so on and so forth. And similarly for all men, you're going to have a total ranking of all women. Okay, so for example, again going with this n over 2 case, so you could have Brad Pitt's preference list being Angelina Jolie, being higher than Jennifer. So I'm just going to use greater than to denote that the thing on the left is ranked higher. And Billy Bob Thornton also has the same rank. And again, note that we cannot make any assumptions about the preferences being same, different. They could all be the same, they could all be different. And let's say for the woman, the preference list is Brad Pitt higher than Billy Bob Thornton for both Jennifer Aniston and Angelina Jolie. So again, for each man and woman, you have a completely ordered list of women or men. All right, just to be sure everyone's on the same page, how many preference lists would you have for n men and n women? N men and n women. 2n, right? So you have one preference list for each man and woman. There are n men and n women. Right? So there are 2n total preference lists. Now, if you were to represent each preference list, say, as an array, that's an array of length n for each preference list, how many elements would you have overall for all the preference lists? You have 2n preference lists. Each preference list has n entries. How many in total? 2n squared, right? Each preference list has n. There are 2n of them. There's 2n squared over. So 2n squared elements in all preference lists. We'll come back to this quantity later on when we're trying to analyze the runtime of the algorithm. This would be a relevant quantity to look at. All right. So finally, we are close, but still not quite there. And we want to define stable matching. And a stable matching S is one, a perfect matching, like we defined over here. And 2 has no instability. So my definition is not complete because now I have to define instability for you also. So let's go with that. I know this is pretty dry, but we have to go through this. I think there's probably only one more lecture that's going to be as dry as this, but it'll become more fun. Okay. All right. So for an instability, you are given a perfect matching. Let's call it S. and you're given the 2n preference lists. Again, one for each n men and one for each n women. And we say a pair m comma w that's not in this perfect matching, that is, they are not matched to each other. So the situation looks like m is matched to some woman w prime, and m prime is matched to w. So these are the ones that are assigned to each other, and you're looking at this pair that is not matched. Okay? So we say such a pair that is not matched is an instability if both prefer each other to their current partners. Okay? So if w is higher than w prime in m's preference list, and m is higher than m prime in w's preference list. Okay? So again, this is a pair that's not matched to each other, but both prefer each other to their currently assigned partners. Okay? So let's do an example that we have been looking at. So let's look at the example. We are looking at same two men and women, and the preference list that is right up here. Okay? And so let's look at the following perfect matching. So Brad Pitt is assigned to Jennifer Aniston, and Billy Bob Thornton is assigned to Angelina Jolie. Maybe talk to your friends for half a minute and see, let me know if there is an instability, and if so, which pair is an instability. Any questions before we move on on anything that we have done so far? Okay, if not, is there an instability in this perfect matching? Okay, some heads are nodding. The answer is yes. So which of the pairs are not stable? Ask your name.
Ryan.
Ryan.
Brad Pitt and Angelina Jolie.
Right, so Ryan says it's Brad Pitt and Angelina Jolie, and the answer is right, but just let's quickly work it out. So Brad Pitt and Angelina Jolie is an instability. Why is that? Well, let's look at the preferences of Brad Pitt. He's currently assigned Jennifer Aniston, but he indeed prefers Angelina Jolie to Jennifer Aniston. And if we go to Angelina Jolie's preference list, she is currently assigned Billy Bob Thornton. but she indeed prefers Brad Pitt over Billy Bob Thornton. Okay? So this is an instability. Is the other pair, Billy Bob Thornton and Jennifer Aniston, an instability? How many think yes? Oh, you have a question? Ask your name.
Tyler.
Tyler.
Isn't Brad Pitt and Jennifer Aniston instability not right?
By definition, an instability has to be a pair that is not already matched. So Brad Pitt and Jennifer Aniston are matched, so by definition, they cannot be an instability. So one way to think about this is, and this is not the ideal way to say this is, but when you say instability, it's not whether the currently matched pairs are kind of unhappy with each other. Is that whether can they be happier with someone else that they're not assigned to. Okay, so is Billy Bob Thornton and Jennifer Aniston an instability? No. So if you look at the thing, they are actually assigned to their most preferred partner, so they're actually happy. All right, good. So after a ton of definitions, we are finally ready to formally define our problem. So this is the stable matching problem. So the input to the problem are the set of men and women, and as I said, we're going to assume that they are of the same size. And you're given two n preference lists. And what you want to output is a stable matching if one exists. So there might or might not be. So if there's not, you should say there's no stable matching. If it is, you should. So what I want you guys to do in the remaining time is to think of the dumbest algorithm you can, which terminates, but it can take as much time as it wants, which will solve this problem. So I give you n men, n women, one preference list for each of the n men and n women, and in a finite amount of time, it could be exponentially large if you want, that the algorithm will decide if there exists a stable matching. If so, it will output 1. If not, it will say there doesn't exist any. Okay? In the interest of time, I have to kind of speed up things slightly. So any suggestions for an algorithm? I have to ask your name.
Try every possible combination until you find one that's stable.
Right. So as I said, I wanted to come up with an algorithm that terminates in finite amount of time, which means in this case, what is the best way to do it? Go through all possible outputs and see if there exists one. So go through all possible perfect matchings S. If S is a stable matching, you stop and you're done. If you have exhausted all possible perfect matchings and none of them are stable, you just output null. Okay? So hopefully you're convinced that this works. However, the problem is there are n factorial possible matchings and this number grows really, really quickly. This algorithm won't even terminate on a computer for n equal to 20. And so Gale and Shapley came up with this algorithm which is much faster. We're going to see how it's n cubed at first and then actually see it's n squared, right? So the moral of the story is, again, smart algorithms will work much better than brute force algorithms. All right, you guys have a good long weekend. I'll see you guys on Wednesday.